Moving on in chapter 6, we're going to really get into the meat of the course today as we find more and more ways to answer questions that before we did with the empirical rule, but now we're going to be able to do all kinds of questions and not just strictly rely on the empirical rule, because the empirical rule had some distinct disadvantages. For instance, if we know we're one standard deviation below or one standard deviation above, we know it's 68.26% of the data. But what if we're a half of a standard deviation below or a half a standard deviation above? We don't know what that is. The empirical rule only does plus or minus 1, plus or minus 2, plus or minus 3. So today, your world is going to greatly expand because you'll be able to do many, many more such problems. You should have gotten a Z chart either from me or online in Blackboard. You should have that in your possession right now, and you will desperately need that as we go through the problems for today. But before we get there, some misleading statistics. Innocent man was accused of being at a crime scene. He denied, but he was facing fingerprint evidence. An expert was called. Prosecution, assuming the defendant did not commit the crime, what is the probability the defendant and the culprit could have identical fingerprints? The expert, 1 in several billion. They're just not going to have the same fingerprint. That solves it, right? Or does it? The defense lawyer says, let me ask you a different question. What is the probability a fingerprint lifted from a crime scene would be wrongly identified as belonging to someone else who was not there? About 1 in 100. When it's lifted, when a fingerprint is lifted, you've seen that on CSI programs all the time. They dust for fingerprints, okay? Dusting for fingerprints is called a latent fingerprint, and there are all kinds of problems with that. In 1995, sorry it's such a long time ago, but it was such a great statistic I had to use it. They administered a test to fingerprint experts. 156 fingerprint experts, okay? They had 4 suspect cards with prints of all 10 fingers. And then they had 7 latents, which are lifted when dusted, as I mentioned. Only 68 out of the 156, 44% correctly classified the fingerprints. Wow. Is that something? Granted, there's no one with a fingerprint like mine, okay? Or yours, right? I understand we all have different fingerprints, but identifying them is a totally different story. Oh yes, one of my favorites. Here's a guy who used to be an undersecretary for food safety at the United States Department of Agriculture, okay? And he's talking about the 80% statistic. 80% of antibiotics sold in the United States are fed to animals. What? 80% of the antibiotics sold in the United States are fed to animals. Do you ever think about that? Is that because we have a bunch of sick animals and we're trying to heal them? No. For reasons that are not fully understood. Scientists, veterinarians, anybody involved in animal science understands the fact that if you feed an animal antibiotics, they gain weight. And nobody fully understands why, okay? So, of course, animals raised in the United States, you get more money for them if they are heavier. We feed them tons and tons of antibiotics, and that is a huge problem because animals, bugs, disease become resistant to the antibiotics. And then you get weird things happening like what we just endured with COVID-19, okay? Anyway, Raymond, this undersecretary for food safety, okay, he writes that he's blaming this 80% statistic on people who just want to get rid of the antibiotic use. Well, of course we want to get rid of the antibiotic use. I don't want to, in my pork chop, be consuming antibiotics. He argues that 87% of the antibiotics used in animals are rarely or never used in humans. That may be so, but you are still feeding massive amounts of antibiotics to animals, and the bugs, the viruses, the germs, the disease that they cause are steadily becoming more and more and more resistant to antibiotics, okay? He says it's a radical step of banning antibiotics in food use. It may be radical, okay? But for heaven's sakes, it would be the smart thing to do. Now, there's something very interesting about this study. It goes back to Mona Calabi's video that we watched a session or so ago. The whole study was funded by the Pork Network. Get it? Raymond's study was funded by the Pork Network. And the Pork Network, of course, wants to promote the purchasing of pork to consume. Okay, so as Mona said, make sure you understand who is sponsoring your study. All right, here we go. Section 2 in chapter 6. We're going to really get into this now. We talked about z-values. Z-values are the number of standard deviations away from the mean. Okay, we know that the area under a curve, a density curve, whether it's the z curve or whether it's your data curve, okay, area under the curve is always 1. The curve extends to both the right and the left, getting asymptotic to the x-axis. In other words, it gets closer and closer in both directions, okay? It's also symmetrical. If it's a z-curve, it's symmetrical about 0 because 0 is the mean for z-values, okay? If it's your data, the curve is symmetrical to your mean. The mean is right in the middle, okay? Most of the area we know, 99.74% of the data is between 3 and -3, okay? Now, and we can go further. As it's shown here in the colors, if you're plus or minus 1 standard deviation, we know that that's 68.26% of the data. Sorry, we have some construction outside the building and you may be able to hear that. We know that plus or minus 1 standard deviation z-value between plus and minus 1 gives you 68.26% of the data. But how about how much of the data is between plus or minus 0.5? We don't know. We don't know. We don't have that information. Wouldn't it be great if somebody calculated all of the various areas so that we could then use those calculations to answer our problems? And someone has. It is done in your z-chart, which, as I mentioned, you should have someplace, okay? It's either on Blackboard, it was either emailed to you, depending upon how you're getting this video, okay? The z-chart is very useful because on the z-chart, the areas are calculated for you. The areas are calculated for you, and now we can do all kinds of amazing problems. For instance, to find the area under the z-curve, you just look in the table. Suppose we know a z-value is -1.25. Now let's talk about this before we go any further. If you recall, z is equal to x, your data item, minus mu, all over the standard deviation, okay? Now, the z-value is the number of standard deviations you are away from the mean. So a -1.25 means you are 1¼ standard deviations below the mean. All right, because it's negative, it's below. Okay, so suppose I wanted this yellow area. This yellow area is the area to the left of a z-value of -1.25. Okay, the chart is constructed to give you that. The chart has a positive side over on the right-hand side. It has a negative side over on the left-hand side, okay? If you want -1.25, okay, you find the z column, identified as Z. You go down to negative 1.2. Go down the column to negative 1.2. Then you run your finger to the left till you get over to negative 1.25. You're under the 0.05 column. And I get an area of 0.1056 square units, the yellow area. Okay? What does that mean? Suppose you're going back to, let's go back to Shy Sam's commutes into the city. Remember doing those problems. And suppose I said, what percent of his commutes are under a certain time? If you do the calculation and get a Z value of negative 1.25, you do this for Shy Sam's commute, get negative 1.25, you can look it up in the chart and you can say that 10.56% of his commutes will be under a certain time. It's an amazing, amazing tool right here, okay? Using this formula, you find your Z value and you look it up, and you always, always, always on the chart get the area to the left, like this yellow region, to the left. Did you all hear that? I'm going to say it again. You always, always, always get the area to the left, okay? So make sure you're with me on that. Suppose Z is 1.92. How could you find the area to the right? Over here, about here is 1.92. How could I get the area to the right? All right, so I'm going to look up 1.92. Now, that's a positive. So you go to the positive side, down the Z column to 1.9, and you go over to the 0.02. So you have 1.92 is 0.9726. Everybody with me? 0.9726, but hold it. 0.9726 is always the area to the left. You want the area to the right, you've got to take 1 minus 0.9726, and I get 0.0274 or 2.74%. 2.74% is the area to the right, okay, because the chart always gives you to the left. How about if you want the area between a Z of negative 2 and 1.35? Here is negative 2, here's 1.35. Let's look them up. Negative 2, simply run your finger down the column, the Z column on the left, to negative 2. I get 0.0228. The area from here and down is 0.0228. Now I'm going to look up 1.35. Go down to 1.3, over to 1.35 is 0.9115. So the area from here and down is 0.9115. Let me check that again. 1.35, 0.9115. Now, I have this area is this. This area is this. To find the area in between, you just subtract 0.9115 minus 0.0228, and I get 0.8887. 0.8887. All right? You can do an amazing amount of work with this formula and your Z chart. You will be doing this for the rest of this course. What if I know the area to the left of a certain Z value is 0.4? So here I am. Here's a Z value. This area right here is 0.4. Can I find this value? Okay, well, sure you can. You can use your chart backwards. I call this a reverse lookup, okay? Instead of going down the columns, right, the Z column, we know the area is 0.4. The areas are what is always in the body of the chart. Okay, so what I want to do is go to 0.4 in my chart and get the one that it's closest to. It should be way down here at the bottom. Way down here at the bottom on the left-hand side, I'm looking at 0.4. It's either 0.4013 or 0.3974. Which one is it closer to? Shouldn't 0.4 be closer to 0.4013 because it's 13 thousandths above 0.4? And 0.3974 is 26 10 thousandths below 0.4? Are you with me? Okay. So I know it's 0.4013. Now let's find the z-value, negative 0.25. Agree? You've got to go out to the right to find negative 0.25. So this z-value is negative 0.25. Okay? How about if the area was 0.5? How about if the area to the left is 0.5? Isn't that dead in the middle? And isn't the mean of all z-values always 0? Right? You can get that from the chart also. If you find 0.5 way down here at the bottom, it's just 0. Okay? Okay. Now, areas to the right have a special notation. Z sub alpha. Z sub alpha is the area to the right. All right? So if I say Z sub 0.04, this means a certain Z value has an area of 0.04. Would be the Z value with an area of 0.04, but it's to the right. Okay? It's to the right. Okay? Can you find Z sub 0.04? Now, if Z sub 0.04 is way over here where this area is 0.04. Yeah? Can we all see that? Yeah, I think so. You can do it two different ways. You can subtract this from 1 because we know the whole area is 1 and we know the chart works just to the left. So if this is 0.04, wouldn't this area over here have to be 0.9996? Whoa, that's not right. Should be 0.9600, I think. Now, all right, 1 minus 0.04. Yes, darn it, it's 0.96, okay? Now, if you know this area to the left is 0.96, can you find the z value? Do a reverse lookup. Look for 0.96. 0.96 is it's on the right-hand side of your chart. And there is the construction once again. Hopefully this is not too annoying. 0.96 is either 0.9599 or 0.9608, okay? And I think you would agree with me it's closer to 0.9599, so the z value has to be 1.75. Everybody with me? 1.75 is this z value. Now, there's another way you can do this. Another way that's actually a little bit easier, okay? Because of the symmetry of the graph, over here, if this area is 0.04, okay? If this area is 0.04, this would have to be a negative 1.75. And you can look it up. Look up 0.04 in your chart. 0.04 is on the left-hand side. It's either 0.0392 or it's 0.0401. And I think you would agree with me it's 0.0401. And 0.041 has a value of negative 1.75. You can look it up and then just make it positive. And you still get your positive 1.75. Okay? How about z sub 0.025? I want the z value that has an area of 0.025 to the right. I could subtract it from 1 and do a reverse lookup. I'm not going to do that. I'm going to go on the negative side and do the area of 0.025. Okay? 0.025 comes out dead even on negative 1.96. Did you find it? And then because the area is to the right, you have to make it positive 1.96. Okay? Much easier. How about z sub 0.05? You could subtract from 1 and do a reverse lookup. I'm just going to look up 0.05. 0.05, 0.05, 0.05, 0.05 is dead in the middle, perfectly in the middle of negative 1.64 and negative 1.65. Take a second, stop the video if you have to. Find it. 0.05 is dead in the middle of negative 1.64 and negative 1.65. So dead in the middle of 1.64 and 1.65 is 1.645. Okay? And negative, but because 0.05 is the area to the right, we know we're on the right-hand side, and you would then make this positive. Okay? Can you find the two z-values that divide the curve into a middle area of 0.95? If you know that this is 0.95, isn't there 0.05 left over for the two outer regions? Okay, the two outer regions. So if it's 0.05, counting both of those, you have to cut it in half, and each one is 0.025. Yeah? Each one is 0.025. Okay, so I'm going to do a reverse lookup on 0.025, and we just did that. 0.025 is negative 1.96 for the z-value here, and positive 1.96 for the z-value over there. Okay. Oh, this is great stuff. Now, use the data in table 6.1 on page 256 to help find z sub 0.9666. So we want z, the z-value that has an area of 0.9666 to the right. We want to be able to do it in two different ways, okay? So I could find the area to the left. If you subtract this, this is the area to the right. So I know that. Here's my data. I know because the total area is 1. This is really close to 1, so I'm way over here. I'm trying to find this z-value, okay? Z-value, 0.9666. You can find the area to the left if you take 1 minus. So if I take 1 minus 0.9666, and I get an area of 0.0334 to the left. So this area right here is 0.0334. Okay? So how can I find the z-value for that area? Do a reverse lookup. 0.0334. 0.0334 is very, very close to negative z-value, negative 1.83. Okay? Negative 1.83. Another way you could do it, 0.0334, since we know it's to the left of the data. If you look on page 256 in your book, page 256, we know they're right at the beginning of the data. You can add 0.0009, 0.0018, 0.008, 0.0227, add those up, and you get 0.0334. So I know I'm 60 and under. Are you with me? This is the other way to do it. I know I'm at 60 and under, so I could use my chart right here. 60 minus the mean, which was 64.4 all over 2.4, and you're going to get negative 1.83. There's the second way of doing it. That's probably harder. It's easier to do it this way. Just look it up. But you could have used that table. All right? Second one. Find the area under the curve for table 6.1 for heights between 59 and 62 in two different ways. 59 and 62. You could do 59 minus 64.4 all over 2.4 and 62 minus 64.4 all over 2.4. Get your z-values. Let's do that. So 59 minus 64.4 equals, divided by 2.4 equals negative 2.25. Do this one. 62 minus 64.4 equals, divided by 2.4 equals is negative 1. Okay? Do a chart. So here we are at negative 2.25, and here we are at negative 1. We want to find the area under the curve, so I got to look these two up. on the chart because the areas go to the left. Okay, everybody see that all right? Look them up. -1, we know is 0.1587. -2.25 is, -2.25 is 0.0122. And subtract. So I have 0.1587 minus 0.0122, and I get about 0.1465. That's the area in there, okay? What's another way I could have done it? Between 59 and 62, look on your table down at the bottom of page 256. Between 59 starts and goes up to 62, you could add up 0.0227 starting at 59 and 0.0450 and up to 62.0757. And what do we get? We get oops, sorry. Extremely close. You're only off by a couple 10,000ths. So you could have done it from your relative frequency chart down at the bottom of page 256, just adding up the percentage of girls that are within those two parameters, or you can use your z-values, okay? Last one, suppose z is -2.78. Find a corresponding height. Okay, find a corresponding height. If you know your z-value, -2.78 is equal to the height. I don't know what that is. The mean is 64.4 over 2.4. Can't you solve that for x? Right? Little simple equation. Okay. Or negative, we can add the relative frequencies until we get that area. The z equal to -2.78 is way, way down here. Okay. So we want to get a z-value of -2. Where's my chart? -2.78. -2.78 is 0.0027. So here we are, -2.78. This area, look it up. -2.78, 0.0027. Now, go down to the bottom of page 256 in your book, and if you add the first two, you get 0.0027, so the height has got to be, the corresponding height has to be 58, right? Okay, a couple different ways you can do that. Oh, love this stuff. There's your homework. You've got one extra problem. Sketch the curve and determine the height when x equals -3.5. That is that very, very ugly formula, right? With the small letter E, okay? So that you should remember that and be able to do that problem.